So before we dive into some of the material today on loss functions and optimization, I wanted to go over some administrative things first. Just as a reminder, the first assignment is due on next Wednesday, so you have roughly 9 days left. And just as a warning, Monday is holidays, so there will be no class, no office hours, so plan out your time accordingly to make sure that you can complete the assignment in time. Of course, you also have some late days that you can use and allocate among your assignments as you see fit. Okay, so diving into the material, first I'd like to remind you where we are currently. Last time we looked at this problem of visual recognition, and specifically at image classification. And we were talking about the fact that this is actually a very difficult problem, right? So if you just consider the cross product of all the possible variations that we have to be robust to when we recognize any of these categories, such as cat, it just seems like such an intractable, impossible problem. And not only do we know how to solve these problems now, but we can solve this problem for thousands of categories. And the state-of-the-art methods work almost at human accuracy, or even slightly surpassing it in some of those classes. And it also runs nearly in real time on your phone. And so basically, and all of this also happened in the last 3 years. And also, you'll be experts by the end of this class on all of this technology. So it's really cool and exciting. Okay. So that's the problem of image classification and visual recognition. We talked specifically about the data-driven approach and the fact that we can't just explicitly hard-code these classifiers, so we have to actually train them from data. And so we looked at the idea of having different, the training data, having different validation splits where we test out our hyperparameters and a test set that you don't touch too much. We looked specifically at the example of the nearest neighbor classifier and so on, and the k-nearest neighbor classifier. And I talked about the CIFAR10 dataset, which is our TOE dataset that we play with during this class. Then I introduced the idea of this approach that I termed parametric approach, which is really that we're writing a function f from image directly to the raw 10 scores if you have 10 classes. And this parametric form we assume to be linear first, so we just have f equals wx. And we talked about the interpretations of this linear classifier, the fact that you can interpret it as matching templates, or that you can interpret it as these images being in a very high dimensional space, and our linear classifiers are kind of going in and coloring this space by class scores, so to speak. And so by the end of the class, we got to this picture where we suppose we have a training data set of just 3 images here along the columns. And we have some classes, say 10 classes in CIFAR10. And basically, this function f is assigning scores for every single one of these images with some particular setting of weights, which I've chosen randomly here. We get some scores out. And so some of these results are good and some of them are bad. So if you inspect the scores, for example, in the first image, you can see that the correct class, which is cat, got a score of 2.9. And that's kind of in the middle. So some classes here received a higher score, which is not very good. Some classes received a much lower score, which is good for that particular image. The car was very well classified because the class score of car was much higher than all of the other ones. And the frog was not very well classified at all, right? So we have this notion that for different weights, these different weights work better or worse on different images. And of course, we're trying to find weights that give us scores that are consistent with all the ground truth labels, all the labels in the data. And so what we're going to do now is, so far we've only eyeballed what I just described, like this is good or that's not so good and so on, but we have to actually actually quantify this notion. We have to say that this particular set of weights, W, is say like 12 bad or 1.5 bad or whatever. And then once we have this loss function, we're going to minimize it. So we're going to find W that gets us lowest loss, and we're going to look into that today. So we're going to look specifically into how we can define a loss function that measures this unhappiness. And then we're actually going to look at 2 different cases, a SVM cost and a softmax cost, or a cross-entropy cost. And then we're going to look into the process of optimization, which is how do you start off with these random weights, and how do you actually find very, very good setting of weights efficiently. Okay. So I'm going to downsize this example so that we have a nice working example to work with. So suppose we only had 3 classes instead of tens of thousands, and we have these 3 images, and these are our scores for some set of W's. And we're going to now try to write down exactly our unhappiness with this result. So the first loss we're going to look into is termed a multi-class SVM loss. This is a generalization of a binary support vector machine that you may have seen already in different classes. I think 229 covers it as well. And so the setup here is that we have the score function, right? So S is a vector of class scores. These are our S vectors. And there's a specific term here, loss equals to stuff. And I'm going to interpret this loss now for you, and we're going to see through a specific example into why this expression makes sense. Effectively, what the SVM loss is saying is that it's summing across all the incorrect examples, so it's summing across all the incorrect scores, classes. So for every single example, we have that loss, and it's summing across all the incorrect classes, and it's comparing the score that the correct class received and the score that the incorrect class received, j minus s of yi being the correct label, plus 1, and then that's maxed of 0. So what's going on here is we're comparing the difference in the scores, and this particular loss is saying that not only do I want the correct score to be higher than the incorrect score, but there's actually a safety margin that we're putting on. We're using a safety margin of exactly 1, and we're going to go into why 1 makes sense to use as opposed to some other hyperparameter that we have to choose there. And intuitively, you can look into notes for a much more rigorous derivation of exactly why that 1 doesn't matter. But intuitively, to think about this, the scores are kind of scale-free, because I can scale my W, I can make it larger or smaller, and you're going to get larger or smaller scores. So really, there's this free parameter of these scores and how large or small they can be that is tied to how large your weights are in magnitude. And so these scores are kind of arbitrary, so using 1 is just an arbitrary choice to some extent. Okay, so let's see specifically how this expression works with a concrete example. So here I'm going to evaluate that loss for the first example. So here we're plugging in these scores. So we see that we're comparing the score we got for car, which is 5.1, minus 3.2, which is the correct class score, and then adding our safety margin of 1. And the max of 0 and that is really what it's doing is it's going to be clamping values at 0, right? So if we get a negative result, we're going to just clamp it at 0. So if you see for the second class score, the incorrect class of frog, negative 1.7, subtracted from 3.2, add a safety margin, and we get negative 3.9. And then when you work this through, you get a loss of 2.9. So intuitively, what you can see here, the way this worked out, is intuitively the cat score is 3.2. So according to the SVM loss, what we would like ideally is that the scores for all the incorrect classes are up to at most 2.2. But the car class actually had much higher score, 5.1. And this difference in what we would have liked, which is 2.2, and what actually happened, which is 5.1, is exactly this difference of 2.9, which is how bad of a score outcome this was. And in the other case, in frog case, you can see that the frog score was quite a bit lower, below 2.2. And so the way that works out in the math is that you end up getting a negative number when you compare the scores, and then the max of 0 clamps it at 0, so you get a 0 loss contribution for that particular part, and you end up with a loss of 2.9. Okay? So that's the loss for this first image. For the second image, we're going to again do the same thing, plug in the numbers. We're comparing the cat score to the car score. So we get 1.3 minus 4.9, add a safety margin, and the same for the other class. So when you plug it in, you actually end up good with a loss of 0. And the loss of 0 intuitively is because the car score here it is true that the car score is higher than all the other scores for that image by at least 1, right? That's why we got 0 loss, that is. So the constraint was satisfied, and so we get 0 loss. And in this frog case, we end up with a very bad loss because, of course, the frog class received a very low score, but the other classes received quite high score. So this adds up to an unhappiness of 10.9. And now, if we actually want to combine all of this into a single loss function, we're going to do the relatively intuitive transformation here, where we just take the average across all the losses we obtain over the entire training set. And so we would say that the loss at the end, when you average these numbers, is 4.6. So this particular setting of W on this training data gives us some scores, which we plug into the loss function, and we get an unhappiness of 4.6 with this result. Okay? So I'm now going to ask you a series of questions to kind of test your understanding a bit about how this works. I'll get into questions in a bit. Let me just pose my own questions first. First of all, what if that sum over there, which is the sum over all the incorrect classes of J, what if that was instead sum over all the classes, not just the incorrect ones? So what if we allowed J to equal to yi? Why am I actually adding that small constraint in the sum over there?
You're adding 1 delta.
Sorry, go ahead.
You're adding the delta to the 1.
Yes. So in effect, what would have happened is the reason that that's a J not equal to yi is if we allow J to equal to yi, then score of yi cancels score of yi. You end up with a 0. And really what you're doing is you're adding a constant of 1. So if that sum was over all the scores, then really we'd be just inflating the loss by a constant of 1. So that's why that's there. Second, what if we used a mean instead of a sum, right? So I'm summing up over all these constraints. What if I used a mean? Just like I'm using mean to actually average over all the losses for all the examples, what if I use the mean over the scores, the score constraints? Go ahead.
If you have too many classes, that would sort of dilute the loss. Possibly.
So you're saying if there were too many classes, that would dilute the loss.
Or like the...
So you're right in that the absolute value of the loss would be lower.
It would actually just be a constant factor.
So it would be a constant factor. Why?
It would be the number of classes, you divide by the number of classes.
That's right. Yeah.
So it's just, any of these choices kind of don't matter for your optimization, right?
Some of these choices matter. But yes, so basically what you're pointing out is if we did actually do an average here, we'd be averaging over the number of classes here, but there's a constant number of classes, say 3 in the specific example, so that amounts to putting a constant of 1/3 in front of the loss. And since we're always in the end, so that would make the loss lower, just like you pointed out, but in the end what we're always interested in is we're going to minimize a W over that loss. So if you're shifting your loss up by 1, or if you're scaling it with a constant, this actually doesn't change your solutions, right? You're still going to end up with the same optimal Ws. So these choices are kind of basically free parameters, doesn't matter. So for convenience, I'm adding a j not equal to yi, and I'm not actually taking the mean, although it's the same thing. And the same also goes for us, for whether or not we average or sum across the examples. Okay, next question. What if we instead used not the formulation over there, but a very similar looking formulation, but there's an additional squared at the end. So we're taking the difference between scores plus 1, this margin, and then we're squaring that. Do we obtain the same or different loss? When you think, do we obtain the same or different loss in the sense that if you were to optimize this and find the best W, do we get the same result? We're not? Yes?
Yeah, because you're thresholding it at 0.
So I like the fact that it's divided. You would in fact get a different loss. It's not as obvious to see, but what one way to see it is that we're not just clearly scaling the loss up or down by a constant or shifting it by a constant. We're actually changing the difference. We're changing the trade-offs non-linearly in terms of how the SVM, the super vector machine, is going to go there and trade off the different score margins in different examples. But it's not obvious to see. But it's not very clear. But I wanted to illustrate that not all changes to this loss are completely a no-op. And the second formulation here is in fact called something we call a squared hinge loss instead of the one on top, which we call hinge loss. And you can use two different, it's kind of a hyperparameter which one you use. Most often you see the first formulation. That's what we use most of the time. But sometimes you can see data sets where the squared hinge loss ends up working better. So that's something you play with. That's really a hyperparameter. But its most often used form is the first one. Let's also think about the scale of this loss. What is the min and the max possible loss that you can achieve with the multi-class SVM on your entire data set? What is the smallest value? 0, good. What is the highest value? Yeah, it's infinite, right. So basically, the scores could be arbitrarily terrible. So if your assigned score to the correct example is very, very small, then you're going to get your loss going to infinity. Okay? And one more question, which becomes kind of important when we start doing optimization. Usually when we actually optimize these loss functions, we start off with an initialization of W that are very small weights. So what ends up happening is that the scores at the very beginning of optimization are roughly near 0. All of these are like small numbers near 0. So what is the loss when all of these are near 0 in this particular case? That's right, number of classes minus 1. So if all the scores are 0, then with this particular loss I put down here, and by doing an average across this way, we would have achieved a loss of 2. Okay? So this is not very important. Where it's important is for sanity checks. When you're actually starting optimization and you're starting with very small numbers W, and you print out your first loss as you're starting the optimization, and you want to make sure that you kind of understand the functional forms and that you can think through whether or not the number you get makes sense. So if I'm seeing 2 in this case, then I'm happy that the loss is maybe implemented correctly, but I'm not 100% sure. But certainly there's nothing wrong with it right away. So it's interesting to think about these. Let's see, I'm going to go more into this loss a tiny bit, but is there a question in terms of this slide right now? Go ahead.
Yeah, summing over j not equal to yi, wouldn't it be more efficient to not do that? So that you can take the matrix and sum over the whole matrix without asking you to remove every row.
Yeah, so the question is, and I was asked to repeat the questions, would it be not efficient to actually not have this ugly constraint j is not yi because it makes it more difficult to actually do these easy vectorized implementations of this loss implementation? So that actually predicts my next slide to some degree, so let me just go into that. So here's some NumPy code for how I would write out this loss function in vectorized NumPy code. So here we're evaluating li in vectorized NumPy. We're getting a single example here. So x is a single column vector, y is an integer, specifying the label, and w is our weight matrix. So what we do is we evaluate the scores, which is just w times x. Then we compute these margins, which is the difference between the scores we obtain and the correct score, plus 1. So these are numbers between 0 and whatever. And then see this additional line, margins at y equals 0. Why is that there?
It's the same as the current.
Yeah, exactly. So basically, I'm doing this efficient vectorized implementation, which goes to your point. And then I want to erase that margin there because I'm certain that margins at y currently is 1, and I don't want to inflate my score. And so I'll set that to 0. Sorry?
Couldn't you just subtract 1 at the end?
Yes, I suppose you could subtract 1 at the end as well.
Very slightly faster cache line.
That's right. So we can optimize this if we want, but we're not going to think about this too much. If you do in your assignment, that's very welcome for extra bonus points. And then we're summing up these margins, and so we get a loss in the end. Okay. Going back to this slide, any more questions about this formulation? And by the way, this formulation, if you wanted to make it, if you actually write it down for just 2 classes, you'll see that it reduces to a binary support vector machine loss. Okay, cool. So we'll see a different loss function soon, and then we're going to look at comparisons of them as well. But for now, actually, so at this point, what we have is we have this linear mapping to get scores, and then we have this loss function, which I've now written out in its full form, where we have these differences between the scores, plus 1, sum over the incorrect classes, and the average across all the examples, right? So that's the loss function right now. Now, I'd like to convince you that there's actually a bug with this loss function. In other words, if I'd like to use this loss on some data set in practice, I might get some not very nice properties, okay? If this was the only thing I was using by itself. And it's not completely obvious to see exactly what the issue is, so I'll give you guys a hint. In particular, suppose that we found a W such that we're getting 0 loss, okay, on some data set. And now the question is this W unique? Or phrased in another way, can you give me a W that would be different but also definitely achieves a 0 loss? In the back?
Yeah, we could scale it with a positive constant alpha or anything.
That's right. And so you're saying we can scale it by some constant alpha, and in particular, alpha must obey some constraint?
Greater than 1.
You'd probably want it to be greater than 1, right? So basically what I can do is if I change my weights and I make them larger and larger, all I would be doing is I'm just making this score difference larger and larger as I scale out W, right? Because of the linear loss form here. So basically, that's not a very desirable property because we have this entire subspace of W that is optimal, and all of them are, according to this loss function, completely the same, but intuitively, that's not like a very nice property to have. And so just to see this numerically, to convince yourself that this is the case, I've taken this example where we achieved previously 0 loss there before. And now suppose I multiply my WI twice. I mean, this is a very simple math going on here, but basically I would be inflating all my scores by 2 times, and so their difference would also become just larger. So if all your score differences inside the max of 0 were already negative, then they're just going to become more and more negative. And so you end up with larger and larger negative values inside the maxes, and this just becomes 0 all the time, right? Go ahead.
Why does the alpha have to be larger than 1?
So the scaling factor would have to be larger than 1 because, let's see.
There's a margin of 1.
Yeah, so there's that added margin of 1, which is complicating things. Yep. Okay. Another question?
Yeah, would the scaling apply to the bias part of W as well?
Would the scaling apply to this to the bias part? So here I guess I'm not assuming the bias for simplicity. But yeah, basically these scores are Wx plus b. So you're just, forget the bias and we're just scaling the W by itself. Okay, cool. So the way to fix this is, intuitively, we have this entire subspace of W's, and it all works the same according to this loss function. And what we'd like to do is we'd like to have a preference over some W's over others, just based on intrinsic, what do we desire of W to look like? Forget what the data is, just what are nice things to have about a W. And so this introduces the notion of regularization, which we're going to be appending to our loss function. So we have an additional term there, which is lambda times a regularization function of W. And the regularization function measures the niceness of your W. Okay? And so we don't only want to fit the data, but we also want W to be nice. And we're going to see some ways of framing that and exactly why they make sense. And intuitively, what's going on is regularization is a way of trading off your training loss and your generalization loss on a test set. So intuitively, regularization is a set of techniques where we're adding objectives to the loss, which will be fighting with this guy. So this guy just wants to fit your training data, and that guy wants W to look some particular way. And so they're fighting each other sometimes in your objective, because we want to simultaneously achieve both of them. But it turns out that adding these regularization techniques, even if it makes your training error worse, so we're not correctly classifying all the examples, what you notice is that the test set performance ends up being better. And we'll see an example of why that might be. Actually, with the next, for now, I just wanted to point out in the next slide. But for now, I just wanted to point out that the most common form of regularization is what we call L2 regularization, or weight decay. And really what we're doing is, suppose W in this case is a 2D matrix. So I have two sums over K and L, the rows and columns. But really it's just all the element-wise W's squared. And we're just putting them all into the loss. Okay. So this particular regularization, it likes W's to be 0, right? So when W is all 0, then regularization is happy. But of course, W can't be all 0 because then you can't classify. So these guys will fight each other. There are different forms of regularization with different pros and cons. We'll go into some of them much later in the class. And I just like to say for now that basically L2 regularization is the most common form, and that's what you'll use quite often in this class as well. So now I'd like to convince you that this is a reasonable thing to want out of a W, that its weights are small. So consider this very simple cooked up example to get the intuition. Suppose we have an example where we are in 4-dimensional space where we're doing this classification, and we have an input vector of just all ones, x. And now suppose we have these two candidate weight matrices, or weight single weights, I suppose, right now. So one of them is 1, 0, 0, and the other is 0.25 everywhere. Since we have linear loss functions, you'll see that their effects are the same. So basically, the way we are evaluating score is by Wx. So the dot product with x is identical for both of these. The scores would come out both of these. But regularization would strictly favor one of these over the other. Which one would the regularization cost favor? Even though their effects are the same, which one is better in terms of the regularization? The second one, right? And so the regularization would tell you that even though they're achieving the same effects in terms of the data loss classification down the road, we actually significantly prefer the second one. What's better about the second one? Why is that a good idea to have? Sorry, can you repeat that?
It takes into account more of your x values in its final result.
That's correct. So, well, that's the interpretation I like the most as well. It takes into account the most number of things in your x vector. Right? So what this L2 regularization wants to do is it wants to spread out your W's as much as possible so that you're taking into account all the input features or all the input pixels. It wants to use as many of those dimensions as it likes if it's achieving the same effect, intuitively speaking. And so that's better than just focusing on just one input dimension. It's just nice. It's something that often works in practice, basically, just the way data sets are arranged. And the properties that they usually have statistically. Okay? Any questions about this? So regularization, good idea? Everyone is sold? Okay, great. So basically, our losses will always have this form, where we have the data loss, and then we'll also have a regularization. It's a very common thing to have in practice. Okay. I'm now going to go into the second classifier, the softmax classifier, and we'll see some differences between the support vector machine and this softmax classifier. In practice, these are kind of like these two choices that you can have, either SVM or softmax, the most two commonly used linear classifiers. Often you'll see that softmax classifier is preferred. And I'm not exactly sure why, because usually they end up working about the same. And I'd just like to mention that this is also sometimes called multinomial logistic regression. So if you're familiar with logistic regression, this is just a generalization of it into multiple dimensions, or in this case, multiple classes, not just two. Was there a question over there? Or?
Yeah, so I was wondering on a higher level why you would want to do regularization. Is it to choose which weight is better given that they have the same loss?
Yes, so the question is, why do we want to use regularization basically? So I don't think I sold it very well. If you're suppose you have this entire subspace of weights that is all achieving the same effects, we'd like to pick between them in some way. And I think what I'm arguing for is that wanting low W's is a reasonable way to pick among them. And the L2 regularization will favor diffuse W's, like in this case here. And one of the intuitive ways in which I can try to pitch why this is a good idea is that diffuse weights basically see this W1 is completely ignoring your inputs, 2, 3, and 4. But W2 is using all of the inputs, right? Because the weights are more diffuse. And so intuitively, this just ends up usually working better at test time because more evidence is being accumulated into your decisions instead of just one single evidence, one single feature.
And to follow up, so you added as a part of the sum, right? To the
That's
loss
right.
function. And so in this case, W2 would have a higher value than W1.
That's right.
So it would have a higher loss.
That's right. So the idea here is that these two W1 and W2, they're achieving the same effect. So this data loss, suppose that that's basically, it doesn't care between the two, but the regularization expresses preference for them. And since we have it in the objective, and we're going to end up optimizing over this loss function, so we're going to find a W that simultaneously accomplishes both of those. And so we end up with W that not only classifies correctly, but we also have this added preference that actually we want it to be, and we want it to be diffuse as much as possible. Make sense? Awesome. Go ahead.
If we want that to be diffuse, why would we use L1 regularization? Can we always use this?
Yeah, so in this particular example, L1 would also be indifferent. L1 has some nice properties, which I don't want to go into right now. We might cover it later. L1 has some properties like a sparsity-inducing properties. Where if you end up having L1s in your objectives, you'll find that lots of W's will end up being exactly 0 for reasons that we might go into later. And that sometimes is like a feature selection almost. And so L1 is another alternative that we might go into a bit more later. Go ahead.
Yeah, doesn't the W1 on the other slide have the nice property? Like, isn't it good that you're ignoring some of the features if they're not actually like giving you a better loss?
Yeah, so the question is, yeah. So you're pointing out that isn't it maybe a good thing that we're ignoring features and just using one of them? Yeah. So there's many technical reasons why regularization is a good idea. I wanted to give you just basic intuition. So maybe I failed at that. But yeah, I think that's a fair point. Yeah. I'm not sure if I have a good return. I would have to. Go ahead.
Couldn't you say that like epsilon 000 would do the exact same thing as W1, or like with epsilon being a really small number? So that vector would do the exact same thing, but it would also have much smaller regularization.
So you want to consider a different W, and you want it to look slightly different from these two?
I'm just saying, like, the previous question was like, isn't it good that we're ignoring some values? So why would W2 be?
Yeah, isn't that a feature, not a bug, that we're ignoring some inputs? Yeah.
So I was saying that you could just have like 0.001 000 as another W vector that would do exactly the same thing as W1 in terms of its decisions, but it would, I don't know, just throwing that out.
I see. Okay. Thanks. Yeah. I didn't want to dive too much into this. There's actually like an entire literature of regularization and looking at the test error and actually writing theorems in learning theory. And you saw some of that in 229. And there are some results on why regularization is a good case in those areas. And I don't think I want to go into that. And it's also beyond the scope of this class. So for this class, just auto-regularization will make your test error better. Okay. So I'm going to go into softmax classifier now, which is just generalization of logistic regression. So the way this will work is this is just a different functional form for how loss is specified on top of these scores. So in particular, there's this interpretation that softmax classifier puts on top of these scores. These are not just some arbitrary scores and we want some margins to be met, but we have specific interpretation that is maybe more principled kind of from a probabilistic point of view, where we actually interpret these scores not just as these things that mean margins, but these are actually the unnormalized log probabilities that are assigned to different classes. Okay? So we're going to go into exactly what this means in a bit. So these are unnormalized log probabilities of all the y's given the image. So in other words, we're assuming that if the scores are unnormalized log probabilities, then the way to get probabilities of different classes, like class K, is that we take the score, we exponentiate all of them to get the unnormalized probabilities, and we normalize them to get the normalized probabilities. So we divide by the sum over all the exponentiated scores. And that's how we actually get this expression for a probability of a class given the image. And so this function here is called the softmax function, if you see it somewhere. It's the e to the element you're currently interested in, divided by the sum over all exponentiated scores. Okay? And so the way this will work basically is if we're in this probabilistic framework where we're deciding that this is the probability of different classes, then it makes sense in terms of what you usually want to do in this setting. We have a probability over different classes. One of these is correct. So we want to just maximize the log likelihood of for the loss function. And we want to maximize the log likelihood of the true class. And since we're writing a loss function, we want to minimize the negative log likelihood of the true class. Okay? So you end up with a series of expressions here. Really, our loss function is we want the log likelihood of the correct class to be high, so negative of it want to be low. And the log likelihood is softmax function of your scores. Let's look at a specific example to make this more clear. Okay, and here I've actually subbed in that expression so that this is the loss. Negative log of that expression. Let's look at how this expression works, and I think it will give you a better intuition of exactly what this is doing, what it's computing. So suppose here we have these scores that came out from our neural network or from our linear classifier, and these are the unnormalized log probabilities. So as I mentioned, we want to exponentiate them first, because under this interpretation, that gives us the normalized probabilities. And now probabilities always sum to 1, so we have to divide by the sum of all of these. So we add up these guys and we divide to actually get probabilities out. So under this interpretation, we've carried out the set of transformations, and what this is saying is that in this interpretation, the probability assigned to this image of being a cat is 13%, car is 87%, and frog is very unlikely, 0%. So these are the probabilities. And now normally in this setting, you want to maximize the log probability, because it turns out that maximizing just the raw probability is not as nice mathematically. So normally you see maximizing log probabilities. And then so we want to minimize the negative log probability. So the correct class here is cat, which is only having 13% chance under this interpretation. So negative log of 0.13 gives us 0.89. And so that's the final loss that we would achieve for this class here under this interpretation of a softmax classifier. So 0.89 for softmax. Okay. So let's go over some examples. Let's go over some questions now related to this to try to interpret exactly how this works. First, what is the min and the max possible loss with this loss function? So that's the loss function. What is the smallest value and the highest value? So I'll give you a chance to think about it. So what is the smallest value that we can achieve? 0. And how would that happen? Okay, good. So if your correct class is getting probability of 1, we have a 1, which we're plugging into the log, and we're getting negative log of 1, which is 0. And the highest possible loss? Infinite. So just as with SVM, we're getting the same. 0 is minimum, and infinite is maximum. So infinite loss would be achieved if you end up giving your cat score very tiny probability, and then log of 0 gives you negative infinity. So negative that is just infinite. So yeah. So the same bounds as SVM. And also this question, normally when we initialize W with roughly small weights, we end up with all the scores that are nearly 0. What ends up being the loss in this case, if you're doing sanity checks at the beginning of your optimization? What do you expect to see as your first loss? Yeah, go ahead.
Log of 1 over number of classes, negative.
Yeah, that's right. So it's negative log of 1 over number of classes. So you'd basically be getting all zeros here. You get all ones here. And so here is 1 over the number of classes. And then negative log of that ends up being your final loss. So actually for myself, whenever I run optimization, I sometimes take note of my number of classes and I evaluate negative log of 1 over the number of classes. And I'm trying to see what is my first beginning loss that I expect. And so when I start the optimization, I make sure that I'm getting roughly that. Otherwise, I know something's maybe slightly off. I expect to get something on that order. Moreover, as I'm optimizing, I expect that I go from that to 0. And if I'm seeing negative numbers, then I know from the functional form that something very strange is going on, right? Because you never actually expect to get negative numbers out of this. So that's the softmax loss. I'll show you one more slide and I'll take some questions. Just to reiterate the difference between them and really what they look like is we have the score function, which gives us wx times b. We get our scores vector. And now the difference is just how they interpret what these scores coming out from this f function is. So either it's just random scores, no interpretation whatsoever. We just want the larger score, the correct score, to be some margin above. The incorrect